All right, welcome back to the constraint analysis series. We're near the end. This video is going to go over how we would conduct our cruise analysis. And the cruise analysis is one tricky component, and that is just accounting for the difference in weight during cruise and our thrust lapse that we would have during our cruise segment. So that would just be thrust setting during cruise versus the maximum thrust, because we're obviously not going to be cruising at our maximum thrust for our aircraft. So then how do you translate that thrust to weight relationship down to our takeoff conditions so that our constraint diagram is all comparing apples to apples at our takeoff condition? So if we think back to our relationships for our cruise, go back to our notes, we have this thrust to weight relationship I'll add here. So our thrust to weight, if we have a desired lift to drag ratio that we want during our cruise segment, then we can just use that. But typically we're given a desired cruise velocity and altitude. So we probably should use this relationship on the right-hand side. Q again is our dynamic pressure. CD naught is our minimum drag coefficient or wing loadings. And then K again is our lift-induced drag coefficient. So that's our 1 divided by pi times the aspect ratio times our span efficiency. So let's start by just coding this in first. And just like I did with climb, I'm going to have the first column just be our dynamic pressure. And instead of sea level, I'm going to put cruise, CR. So I think that will help just make our equation a bit easier. And if we make mistakes, it'll be easier to spot that. So for our dynamic pressure, this is equal to 1/2 times rho times our velocity squared. Now in this case, our velocity is going to be our true airspeed at cruise. So I'm going to take this value up here, and I'm moving it to our cruise speed from our requirements. So we have that up here. Where is our cruise speed? Cruise altitude, cruise speed, VC, right here. So that 286.67 knots true airspeed. So we want this. And then the thing that's going to be changing is our dynamic pressure. I guess our velocity isn't changing. We don't need to change this for each value. Maybe I'll just calculate Q as cruise. Let's do that, instead of wasting a whole column. I'm going to drag this down, add some space. Cruise dynamic pressure. This will be Q. And this is equal to 0.5 times our cruise velocity times our density of cruise, or velocity squared rather, times our density of cruise. So our density of cruise, we calculated that already from our atmospheric model. Move this out of the way. Love Excel. I want to click on one of these cells. So we want to click on this cell right here. That's our cruise condition. Let's go back and correct this times this cell here, our density in our cruise condition. So we have our dynamic pressure, and we'll add the units later. So then our dynamic pressure is here. We can simplify our equation for cruise. So I'm going to do our cruise segment. And I'll put in our altitude just as a reminder. And we're calculating this as thrust to weight. That's the result of this column, and that's going to be at sea level. So then our equation becomes, delete all this, our dynamic pressure times our minimum drag that we have, so CD min, divided by our wing loading. So our x-axis over here, times our wing loading, or sorry, plus our wing loading, times our induced drag coefficient k divided by our dynamic pressure q again. So we have this. I'm just going to make some of these values constant so they aren't changing as we complete the row. So this is our thrust to weight ratio. If we weren't to consider our thrust lapse during our cruise condition, and if we were to ignore our weight change during our cruise condition, because our aircraft's obviously going to, lose quite a bit of weight during the cruise segment. So we're not accounting for that, since thrust just has to overcome, in some flight condition, has to be enough to overcome the drag, and the drag is dependent on the lift that's generated, and the lift that's generated is just dependent on the weight of the aircraft just to maintain level flight. So that thrust requirement is going to change during our cruise segment, so we have to find a way to normalize this. So let's see what this looks like if we were to not consider those things. Let's plot these values. So I'm going to add our cruise. Let's say no consideration for takeoff conditions. Let's say not takeoff condition. Our x values are our wing loading values. Let's come over here. And our y values are thrust to weight values. So when we plot this, we see this relationship up here. So as it is right now, our rate of climb and our, it's hard to see with these colors, our climb gradient relationships are sort of our limiting factors. Let's see if that's what that is. These are kind of what is dictating our flight so far. So let's now adjust our thrust to weight ratio and account for things like our weight and our thrust lapse. So I'm going to copy over this column. I'm going to plot them all together so we can see the difference. So this time I'm going to have our thrust lapse and I'm going to set that equal to 0.5. So you can use the figure from our notes, which is from the Raymer text, which gives a suggested thrust lapse based on a high bypass turbofan, traveling at Mach 8, so we are traveling at a much lower speed in our RFP. But I'll just copy it here so you can see what I'm referring to. So this figure here is just showing the typical thrust max during takeoff versus the thrust during dry cruise. So in your cruise condition, you don't require as much thrust, so that thrust is going to decrease depending on the altitude at which you're flying. So you can see that this ratio, take the maximum value at sea level versus the maximum value up here, that will indicate the amount of decrease. So if we're traveling at 50,000 feet, 60,000 feet, maybe we extrapolate this a bit, it's about half at this point of the sea level condition. So our lapse might be 0.5. Again, this is just an estimate to see the effect of our lapse in our cruise condition, but for turbojets, turbofans in particular, maybe somewhere between 0.2 and 0.5 from the text might be reasonable as first guessed. I think it says typically that the transport aircraft have a cruise thrust of around 20 to 25% of the takeoff thrust. So that would be a thrust lapse of 0.2, 0.3. So let's just see the effect of having 0.5 because we're not traveling at Mach 0.8. So I have that parameter over here. It's originally set to 0.6. I'm going to change that to 0.5. Just so I can see this I'm just going to change thrust lapse to just lapse, 0.5. The next thing we have to consider is the change in weight. So I have this cruise weight fraction based on my my weight analysis that I did before. So the weight at the end of the cruise segment versus the initial weight is only 68%, or 0.68. So what we can do is take in consideration the average weight of the aircraft over the cruise segment. So I'll show you how we include that. So this again is a relationship from the Ringway textbook that we looked at in our notes. We want to convert the cruise condition, which we already calculated, to our takeoff condition. So what we're going to do is we're going to divide by our lapse, so our thrust during cruise over our thrust during takeoff. So we divide by T cruise over T takeoff, which is 0.6, same as multiplying by 1 over 0.6. So this will make the thrust to weight value larger, because if we have a thrust to weight required for cruise, that means we need more thrust to weight because we're not operating at full thrust to weight. So this will increase the value. But then we multiply by our cruise weight divided by our takeoff weight. That will decrease our value that's needed because our aircraft weighs less. So it's decreasing our thrust requirement. So let's add these two things. We're going to multiply by these two factors. I'm going to take this entire relationship, I'm going to change it back to D column. Everything shifted over one column, so let's fix that. So now it's back to the right values. And then I'm going to pre-multiply by these two things. So our lapse rate, 1 divided by our lapse rate, gives us the thrust during takeoff divided by our thrust during cruise. And then I'm going to multiply by our average cruise weight fraction. So our average cruise weight fraction would be the fraction at the beginning of cruise minus the fraction at the end of cruise divided by our gross weight. So it's just the average of these two weight fractions. So I'm just double checking I have this. So I believe, yeah, in my notes, this is actually the average, yes. So this is the average weight fraction during our cruise segment. Oh, I lost everything, great. Let's repeat this. So we're going to multiply by 1 over 0.5, which is just 2, and we're going to multiply by our cruise. And I just need a bracket at the front, and everything should be highlighted good. Add our dollar signs. And so now we have a representative thrust to weight ratio that accounts for the average weight during our cruise segment. And now if we plot this, depending on, a few things, the altitude that you're flying at and the weight lost during your cruise segment, it would have a either positive or negative effect on this thrust. If you're losing a huge amount of weight during your cruise segment at a lower altitude, then this might decrease your thrust requirement. But if you have a low loss in weight during cruise, so it's not too much of a difference, and you have a high altitude cruise, so a large thrust lapse, then this might make your requirement more stringent. So we'll put cruise, and we'll put takeoff condition. So again, our wing loading is our X value, and our Y value, thrust to weight. So because we're flying at such high altitude, this is actually making our cruise requirement for thrust to weight much more stringent. Now this again is based on a lapse rate of 0.5. So now that we've parameterized this, I can just change this value to 0.4. We can see as our lapse decreases, our thrust requirement becomes higher and higher. And you can see up here, now we have quite a large thrust requirement. If we're going to try to match our stall condition, we need a thrust to weight ratio of about 0.5 so that we could operate at 20% of our take sea level thrust during our cruise condition. So we make this 0.3, say. Then now our optimum point, if we're trying to minimize thrust to weight ratio, could be somewhere here, but that would mean we have to go with a wing loading of 12. So that would require quite a large wing for the weight of the aircraft that we have. So maybe it's more optimal to choose a higher thrust loading to reduce the size of the wing. We have to kind of do trade-offs now at this point. These are our two design points that we would look at. We've got to figure out which one is actually going to deliver the best design, and there might be two design points that you have to go further down to do more analysis on. If we can get away with a higher thrust lapse, then this brings us down here and we kind of remove this problem. It also depends on that average weight. So your average weight that you calculate during cruise, again, is just the average of your weight fractions at the beginning of your cruise segment and the end of your cruise segment. It's a pretty simple calculation if you've done your weight analysis. So that's pretty much it for cruise. Once you get those things plotted, all you have left to do is your landing. And then once you have your landing, you have a completed constraint analysis diagram. You can play around with the parameters for your aircraft to try to pick values that you want to solidify and continue doing further analysis with. So in the next video, the last video, we'll look at just how do we plot our landing condition. And again, we'll do that based on the approximations presented in Reamer.